Hello, everyone. Welcome to my second lecture. It's the second lecture of the week, as well as the second lecture by me this time. And as you probably can hear, the audio is much better. So, in order to make this more pleasurable for you, I decided to invest in a new microphone. I hope you enjoy. The topic of this lecture is approximation using sequences. Um, so, here first a short outline about what we're gonna go over. First of all, of course, I will introduce you to the concept of approximating numbers with sequences, with rational number sequences, and then we will put most of our attention into developing two methods for approximating numbers. One is called the Babylonian method, and the other method is called continued fractions, and we will go over them, find a few examples, and discuss why they're useful. So, before we start with actually talking about sequences, we have to take a look at the properties of different sets of numbers, because this is kind of the baseline motivation of what we're doing here. I've written down the definition of a rational number. It is that it can be expressed as a fraction of two integers, a over b. This includes obviously all integers, but also most useful numbers we can do. And by this, we can also express very odd, ill shaped, many decimal places numbers. In fact, a mathematician would say that the rational numbers are dense on the number line. This means that um, if you take two arbitrary rational numbers, it doesn't even matter how close they are to each other. Like they can be arbitrarily close to each other. There's still infinitely many more rational numbers in between them. All right. And one thing to bear in mind is that rational numbers are what computers work with. So computers basically only have discrete memory, and they express decimal numbers with rationals. So by the fraction of two integers. This is important to keep in mind. Computers can't do more than rational. Now, however, we have the problem that in mathematics, most numbers are not rational. In fact, there's a lot of very nice proofs showing that almost every number is irrational. Irrational means it cannot be expressed as the fraction of two integers, and in practice, this means that if you write out the number as a decimal number, you get infinite and non-repeating decimal places. Whereas for a rational number, you either get finite decimal places. So, for example, a quarter would be 0.25, or you get repeating decimal places. So, for example, 2/3 is 0.6666, and this repeats on forever. Whereas with irrational numbers, those are non-repeating. Now, if we take the set of rational and irrational numbers together, this gives us the real numbers. The real numbers is usually the one set almost every operation in mathematics is carried out. So if you have any statement, any theorem, any calculation, anything at all, really, and the set of numbers we're working on is not specified, it is the real numbers. This is not because we like working with those nasty irrationals. After all, the rational numbers already are dense on the number line. The reason is just that the real numbers have quite neat mathematical properties which we like to utilize. But there will be more regarding this later on in the course. Now, our main issue with irrational numbers is that we don't know where they are. So let's take, for example, pi. We know pi is irrational, incredibly difficult to prove, but it is irrational. We know it for a fact. Um, This means we cannot express it as a over b. But now the question is, how do we find pi on the number line? How do we find square root of 2 on the number line? Irrationality of the square root of 2 was already mentioned in last week. So this is where we want rational approximations. We want to go ahead and find a neat, nice, easy to write down, easy to memorize rational number with all the friendly properties of rational numbers that is as close as possible to our irrationals. So we basically do the trade-off of our number is friendly and well-behaved for the trade-off of it's not the exact number we're looking for. Let's look at a more concise way of phrasing that. Here we have two definitions. First of all, we define what an approximation of a real number is. So let's say x is a real number, then a is our approximation. And now the question is, how close do you have to get in order for it to be an approximation? Well, the answer is you practically choose. Usually we just say epsilon. This is just the distance we are allowed to be from our real number. This is, of course, arbitrary. Like you can pick epsilon to be 10, usually not very accurate, or 100th, completely up to you. And we call a an approximation of x if it is within that distance. And the second definition we're looking at is defining an approximation sequence. We will later on see that using approximation sequences is very useful in order to get actually good individual rational approximations. So an approximation sequence is a sequence of numbers that has two properties. First of all, it converges towards our target number x. And secondly, each constituent of our series, each term, is closer to x than the previous one. It can be that one is above x and the next one is below it, but the point is you have to get closer every step. And if you get closer every step, then you have an approximation sequence. All right, I hope that the definitions are clear now. If not, then going further into the video, you might want to just go back and check them in order to be safe. We will now discuss two important methods of creating such sequences. All right, so I will just pick a number now. I will pick good old root 2, which is nice, simple, small. We roughly know its value and we know it's irrational. And I will construct a method to iteratively approximate it. First of all, we have to start with two initial values, and they need the following property. They need the property that our target number, root 2, is within the interval that is bounded by them. So we conveniently know that root 2 is somewhere between 1 and 2, so we can just pick 1 and 2. For the method I'm discussing, this is an important prerequisite. If it is not given, then before you can actually start doing the method of approximation, you have to find an interval which entails your target number. This interval has the length of 1, which is, I would say, rather short, but it really doesn't matter. Like, your interval can have the size of 1,000. The method works nonetheless. You just have to find an interval of which you know that your target number is entailed in. Okay, so now we have the interval of a length 1, and our goal is to shrink it. So we want to iteratively make the interval smaller and smaller, but keep the property of having root 2 in the interval. For this, we'll just split it in two parts. So we will cut the interval apart in the center, and we will check is our center number smaller or larger than our target number? And if the arithmetic mean, so basically the average number between 1 and 2, the central number, is smaller than root 2, well, this means that root 2 is larger than 1.5, and it has to be in the upper interval. And if root 2 is smaller, this means it has to be in the lower interval. By doing this comparison, we can discard half of our interval and approximate root 2 twice as well. So I've written down the calculation. Our arithmetic mean here is 3 over 2. We square it in order to be able to compare. So the point is, root 2 is an irrational number, and we don't really know where it is on the number line. But if we square it, we get an integer, and we know quite well where 2 is on the number line. The point is, if we have two sides of an equation or of an inequality, we can square it if both sides are positive without disturbing the inequality. So imagine we have 3 is smaller than 5. If we square both sides, the inequality still holds. So this means that squaring is a transformation of an inequality which is invariant. So it keeps the property of the inequality. So what we can do is we can square 3 over 2 to get 9 over 4. And now we compare this to the square of our target number. And 9 over 4 is larger than 2. This means that 3 over 2 is larger than root 2. Okay, what does this mean? This means that root 2 has to be in the lower interval, since it is smaller than our mean. So now we discard the upper interval, and we're left with the interval of 1 and 3 over 2. And basically, that's it. Like, this is full stop, and now start at step 2 again. You repeat this over and over until you get to an accuracy which satisfies you. Here I created a little chart which visualizes the next steps. You start with an interval of length 1, and you iteratively discard the half of the interval which does not entail the number you're looking for. So here you see the red boxes, they are the discarded intervals, and the green boxes, they are the kept intervals. And this can keep on going for an arbitrary amount of time, and we will get closer and closer to the actual value of root 2. If you find this visualization helpful, you can always go back to try and internalize it. I usually find such ways of explaining a method much better than a long list of steps you perform in your algorithm. What we just did is called the Babylonian method, or sometimes the Heron method. We get two number sequences as a result. The first one is called the Heron sequence, named after the Greek mathematician who allegedly came up with this. And this is the important sequence. So these are the numbers on our number line, which are the arithmetic means of our intervals. It can be debated whether your initial number 1 should be in there or not, but that's really not important. The point is that you just make a sequence out of your arithmetic means. And since every single time you create a new arithmetic mean, your total interval length shrinks to half. This also means that every new term in your sequence is closer to root 2 than a previous one. This means, should this converge to root 2, we get an approximating sequence. Okay, but is it really an approximating sequence? Well, in order to do so, it has to converge towards root 2, right? So in order to show this, we will look at the second sequence, and this is the sequence of interval lengths. The sequence of interval lengths we can easily deduce is just 1, a half, a fourth, an eighth, and so on, since we're halving the interval length every time. And this clearly converges towards 0, right? It's less and less. And the limit of it actually is 0. If you've never heard this before, this might sound counterintuitive, since this sequence obviously never actually becomes 0. But this will be discussed in more detail in chapter 3. Infinity is sometimes a tricky concept. And so the point is, since our interval lengths converge to 0, our intervals converge to a singular number, right? Because an interval of length 0 is just one number. And since root 2 is always within the interval, because we pick the interval root 2 is in, this means our initial sequence, the Heron sequence, has to converge towards root 2. I think this is a pretty elegant way of showing that your approximation converges. And since it does, this means that here at hand we have a rational approximating sequence for root 2. All right, I hope you got to the lecture fine so far. If you want, you can take a small break right now. And while at it, if you want, solve a small sample exercise. You're supposed to calculate the rational approximation of root 3 with an accuracy of more than 1/10. So it should be more accurate than 1/10. And to do so, you're supposed to use the Babylonian method. Just take your time, take a sheet of paper and a pen, try to solve it. And if you want to know the solution to it, just stick around. I will discuss this after the lecture. Now, time for a little remark right here. Aside of all the rational approximation business, if we look at the last method, we needed to make a size comparison between our irrational number and our arithmetic mean. So we had to compare root 2 to 3/2. And this works, right? Because we can square root 2 in order to get an integer, and these numbers are easily comparable. Of course, ignoring the fact that you can use calculators, right? We're doing this in a mathematically rigorous way on a sheet of paper. And this actually poses a problem for the thing we're doing here. Because there are some numbers, like pi, for example, where you can't do that, right? So you're squaring root 2 and you get an integer, which is easy to compute. But for pi, you don't really have a way to do any manipulation of it in order to get a rational number, which is easy to compare. Squaring pi just yields another weird irrational number. And if you make a manipulation of pi which includes an irrational number, then the point is if you also have to manipulate the other side of the equation, and if you manipulate the other side of the equation with an irrational number as well, then your other side of the equation is irrational, right? So if you divide by pi, you get 1, but then on the other side of the equation you have divided by pi. So this doesn't really help you to solve the inequality. So this is a very problematic thing. This property in mathematics is called transcendentality. A number which has this property is called transcendental. This means by sheer manipulations of addition, subtraction, multiplication, taking the power off, with other rational numbers, you can't get to a rational number. It always stays irrational. And knowing this problem, we do have to somehow adapt our methods in order to overcome it. Well, the point is, finding pi on the number line is a really difficult problem. Like, it's really difficult. And it took time until, I think, the 19th century for us to get approximations better than 10 decimal places. I mean, nowadays with strong computers, we know billions and billions of decimal places, but back in the day, this was quite difficult. So, since we're using old mathematical methods, nothing new and modern, we will just assume that we know the irrational value of pi. The value of pi will be whatever our calculator tells us. We will see that for the next method, which is quite useful, we need to have an idea where pi roughly is. But, well, in return, we get a really, really good method. Okay, so let's take a second to reflect on what was missing with the Babylonian method. An issue with the Babylonian method is that it always converges with the same speed. That is, every new step halves the size of the interval. But imagine your number is at the very, very end or the very, very beginning of your interval. Then you would like to cut off the majority part of the interval right away without having to do it over and over and over again in the middle, right? So you want to chop off more than just half of your interval. And in a sense, that's what we're gonna do now. What we're looking for is the following. If we have a rational approximation of a real number x, of course, it's an epsilon environment, it is the best rational approximation if there is no number with a smaller denominator which is closer to x. So assume we want to approximate root 2 again. There we had the approximation of 11 over 8. Is 11 over 8 really the best approximation? It only is so if it is the closest number to root 2 among all possible numbers with a denominator smaller or equal to 8. So I don't know right off the top of my head if it is a best approximation, but especially when your approximations get more precise, the Babylonian method almost never yields best approximations, just because it isn't designed to, and if it does so by mere chance. But the following method, which we're exploring right now, will have this property that it always finds the best approximation of an irrational number. Okay, so the method is called continued fractions. And the baseline idea is to generate a continued fraction. And what is a continued fraction? It's a fraction where you expand the denominator iteratively by more and more fractions. So you start out with, for example, 1 over 3, and then you say 1 over 3 plus 1 over, let's say, 4, plus 1 over 2, plus 1 over 17, and so on. So you, in each iteration step, you take the denominator, which is some integer number, and then you add another fraction to it. So you always put a new additional fraction into the denominator. All right. So let's see how we can create a continued fraction for pi. The algorithm goes as follows. We first of all have to separate the parts before and after the decimal place. So for pi, the number before decimal place is 3. We know this. And we memorize it, right? This is important for our continued fraction. And now our approximation works with this rest bit, right? The thing we cut off. And we calculate the first denominator in our continued fraction with the following calculation. So we take the floor function of the reciprocal value of the rest of pi. This is just complicated mathematical speak for the first equation you can see on the slide. Floor function just means this weird brackets that only have like a bottom part. This just means rounding down. So we get some weird number with a lot of decimal places. We just round down to the next smallest integer, right? And reciprocal just means you take 1 over something. So the rest of pi when we deduce 3 is about 0.1415 and so on. And if we plug this into a calculator, it gives us about 7.0625 and so on. So the floor function, this is just 7, right? So this means we get our first continued fraction. We get the first term, which is 3. This is just our integer term in front of the continued fraction. It's not part of the continued fraction. And then the first fraction is 1 over 7. So this is the first term. This is our first approximation. And it yields 22 over 7. And this is already a very good approximation. If you just plug it into a calculator and subtract pi, you'll see it's estimating it correctly to about 100th, which I think is pretty amazing for such a small number. Like 22 over 7 just has small numerator, small denominator. Pretty amazing stuff in my opinion. Okay, and for the next step, we again have to take the rest, but we are now not taking the rest of our approximation, but we're taking the overshoot of our last calculation that we cut off, right? So we put the floor function on 7.0625 and cut off the 0.0625. So we use this rest now to continue calculating, right? So our second fraction is the floor function of the reciprocal value of 7.0625 minus 7. So it's 1 over 0.0625 and so on, which yields almost 16, but not quite. It yields 15.9965 and so on. And this is equal to 15 if we floor it. Okay, so like this, we get to our second continued fraction. And this is 3 plus 1 over 7 plus 1 over 15, which if we put into a single fraction is 333 over 106. And if we put this into a calculator, you get within 1,000th of the actual value of pi. And this already looks quite good, right? Doesn't it? You already got to 1,000th just by computing 3 approximations. 3, like the integer 3 being the first one. Whereas if you remember with the Heron method, you were only halving the accuracy of your method in every step. Okay, so now we're getting to the second sample exercise. If you feel like it, you can try now and calculate the fourth continued fraction of pi. So just calculate the next step. And I would ask you, if you do so, to determine the epsilon distance to pi. So determine how far off it is from pi. This will give you a pretty amazing result. Like, I don't know how excited you are about rational approximations, but if you are, this will probably blow your mind somewhat. But like, heads up warning, you do need a calculator. It kind of has to be accurate, but like probably any computer or phone calculator will suffice. But there's like no chance whatsoever of doing something like this by hand. Now let's quickly discuss the sequence that we get from this operation. The sequence is just the sequence of numbers which our approximation yields. So we start with 3, and then we get 22 over 7, 333 over 106, and so on. This is also a convergence sequence. And the reason it converges is that every new term is smaller than the previous one, and at the same time we have an absolute lower bound by pi. So our sequence is monotonous, as we would say, but it is bound from below. This means it's always going down, but there's a bound that it's never exceeding, so it must be converging there somewhere, right? It's never going back up, but it's also not exceeding the threshold, so it must converge. Why this works and how you could use this to prove convergence of any sequence, you will learn in the next chapter by Leo. Okay, so this sequence is far more difficult to obtain than the Heron sequence. It takes a lot of computational effort. You have to know your formula, and you have to be quite accurate to a lot of decimal places in order not to make a mistake. And additionally, you need to know where your number to be approximated actually lies on the number line. So here our goal is not to nail down the number on the number line, but just find a rational number which is close to it. Like we already have an idea where our number is, but we want to get a real good rational number which we can use in our calculations, which is really close to it. So imagine you get like a 3-digit rational number, which is almost exactly pi, then whenever you're calculating something, you don't have to use 3 or 3.14 or 314 over 100, but you can use your really good rational approximation. So you get a very small error, but you can still calculate by hand. So obtaining such a rational approximation still has value, even if we know where the number is on the number line. Luckily for us, we don't have really to worry about knowing the exact value of pi, courtesy of modern calculators. We know it to billions of decimal places. But now, all these downsides, they are now really alleviated by the fact that we get best approximations. We're not proving it here, but every single approximation here we get is a best approximation, meaning there is no rational number with a smaller denominator than the ones in our sequence that are closer pi than the numbers in our sequence. Take, for example, our third term. It is off by less than 1,000th, whereas the Heron sequence at this point can be off by as much as 0.0625, which is about 6%, assuming the initial interval to be 1. So we are far more precise. Okay, time to wrap things up. So, what did we learn today? Rational approximations are quite a useful concept. They are directly related to number sequences because they utilize number sequences to prove convergence and to prove that they really get arbitrarily good approximations. And in return, knowing your theory of number sequences can be quite useful to obtain good rational approximations should you need any. If we have an approximation algorithm, the important properties are that they have to converge towards our target number, and they must be bound. And even though we only discussed 2 methods, there's like plenty of methods to get approximations. And depending on the actual problem at hand, it might be that the 2 methods I presented to you are quite useless, and some other method is really good. But the mathematical concept is always the one we discussed. The Babylonian method is a very, very old method. Um, it was used back in the day when people still did not believe that things like irrational numbers exist, but they still used it to approximate numbers they couldn't express as rational numbers. Um, Quite a strong algorithm, but well, simple and strong, um, not very accurate, right? It doesn't really take any advantage of the properties of nominators and denominators. It always has a power of 2 as a denominator. It's kind of sticking to that, right? It always increases the denominator, and according to the denominator, it tries to find the correct nominator, but it doesn't really care about finding a good denominator, right? The denominators are pre-given. And we improved on this by using a continued fraction algorithm. Continued fractions are a quite powerful concept in mathematics, which are used for many other things, also far more advanced things. But the algorithm we looked at allows us to also create an approximating sequence, and one that gives us always best approximations, which is pretty amazing in my opinion. All right, we're already at the end. Glad you made it so far. Now, if you solve the 2 sample exercises, I'm glad to discuss the solutions with you. If not, you still have a chance to pause the video and do them if you like. All right, here we go. For the first exercise, you can again assume 1 and 2 as initial values, as you probably know that root 2 is smaller than 2. So we perform our initial step, and we find out that a root 3, I'm sorry, is larger than 3 over 2. So our interval is shrunk to 3 over 2 and 2. Now here the arithmetic mean is 7 over 4. And now our interval length of the 2 resulting intervals is still a quarter, right? It's 0.25, which is more than the epsilon value of a tenth. However, we could still take 7 over 4 as a rational approximation and check whether we're already good enough, right? So might happen that we're lucky. And if we calculate it, well, usually how the calculation works is you square both numbers, take the difference, and then take the root. You get that the difference of the two is 0.0179, which is like really close, right? This is a pretty lucky approximation. So this means that 7 over 4 is already sufficient to solve the exercise. Okay, now to exercise 2. We are supposed to calculate the 4th term of our continued fraction sequence. For this, we need to bear in mind what our previous reciprocal was. It was 15.99 and so on, leaving us with a rest of 0.99. Okay, so we plug this into a formula for the 3rd fraction. So we get the reciprocal value of 0.99 and so on, which is, of course, almost 1. So if we take a floor function, it is just 1. So we get a new continued fraction where in the denominator of 15, we just add a 1 over 1 or a 1. Kind of makes sense to write 1 over 1 because the next term will be 1 over 1 plus something. All right, and this gives us the value of 355 over 113. And now comes the amazing bit. If you plug this into a calculator, the difference between your approximation and pi yields 0.000002667 and so on. So this means A3 is accurate with respect to a third of a 10 millionth to pi, which in my humble opinion is pretty amazing, right? You get a 3-digit rational number, 3-digit nominator, 3-digit denominator, and you're approximating pi with an accuracy of well over 1,000,000. So, pretty powerful method, isn't it? Okay, thank you for sticking around and see you in the next lecture. Take care.